So, hello everyone. First of all, I would like to thank Sams for this great event and the opportunity to be here to talk to you today. Okay, so let me introduce myself. Well, I'm not gonna be too long. Okay, you can find me on LinkedIn. My name is Thiago. I'm speaking from Brazil. Woohoo! And I'm currently working as a senior digital investigator and forensic analyst at IBM. Okay. So moving on, I'm here today. Oops, sorry. I think I clicked it. Okay. So moving on, I'm here to talk about how to fast triage. Okay, Unix-like systems using the UAC tool. In the first part of this presentation, I will basically show how UAC works, and then we're gonna jump into analysis of a compromised Linux system, okay? So let's suppose you are working on an incident response engagement where you are connected to a VMsphere server, and then you were trying to triage your system, and boom, you try to extract some information, and come on, vSphere should be or similar to a Linux system, right? So another one, you are triaging a FreeBSD, and you go to Slack proc, no proc FS. Come on, they used to be all Unix-like systems, right? And then you are triaging a Solaris, okay, system. And you try to copy and paste your comments from your notes. And again, some options are not even accepted or available on some native commands. So come on, you start get nervous in front of your customer, right? Doing your triage and engagement. The last one here is concerning the PS. So Linux is Linux. All Linux are similar to each other, right? So no, some of them are so small or embedded Linux systems that they don't even have the common options in PS, for instance, the -E or -EF. They are not even available. So how many of you already faced on this situation before? Imagine you are in front of your client trying to extract information from his server, and you need to go to Google, need to go to your notes. It's not good, right? So there's a lot of good tools out there for data collection and triaging, but sometimes you can't just deploy EDR solutions and client server-based solutions. In the environment, you just need a quick triage for your Linux or your Unix system. So what is UAC? It's basically a shell script that makes use of native binary tools to collect artifacts. UAC was created to facilitate and speed up data collection for quick triage. So no installation is required. It's not depends on dependencies or packages. You can even run UAC from a USB device or a network share. Okay. Oops. UAC supports most of Linux systems. Okay, most of the Unix-like systems like Android, AIX, vSphere, FreeBSD, Linux, a lot of systems. I have been even testing UAC on small routers like OpenWRT or network-attached storage devices like QNAP, Synology. Okay, they are Unix-like systems, workstations, servers, even in different architectures, because UAC is architecture independent. So you can run on PowerPC, Spark, or even on Linux running on mainframes. So I left here the project page and the project documentation page for you guys. So how UAC works behind the scenes. First of all, UAC will check for the available system tools. This is where UAC checks for if tar is available, if gzip is available, if stat is available, what options the find command supports on the target system. Then UAC will load the configuration file. It will build a list of artifacts to be collected based on the options you provided on the command line, and we are going to see this in a few. Then UAC uses a couple of collectors to triage or to collect data from the server. So there's basically 5 collectors. The command collector will be used to run commands on the system and store the output into text files. The find collector is used to find files and store the output into text files as well. So if you are trying to find executable files, trying to find hidden files, this is the collector that does that. There's the stat collector, which collects file system metadata information using the stat command. There's the hash, which like the name says, will hash files for you using one of the hash algorithms that you set in the configuration file. And the last one is the file collector. This one will just collect raw files for you. So you can set UAC to collect the /etc/var logs, and the raw files will be collected and will be stored in the same path structure in the output file. Okay. For more information about the collectors, what options you have, please go to I invite you to visit the project's documentation page. Okay. And then after the collection, UAC will create an output file, will hash that output file, and will create an acquisition log for you. So let's see how is the artifacts in UAC. So UAC has what we call artifacts file. So the artifacts file is used to define parameters that will be used to collect data. Okay, so they are basically YAML files located in the artifacts folder, and UAC will read those files on the fly, and based on their contents, will collect the data for you using one of the 5 collectors. So an artifact file, we have the list of artifacts and then the artifact definition. Okay. Here's some examples. So as you can see, artifacts will run on predefined operating systems. Okay. So the first one will only run on vSphere, right? Artifacts will also be collected using one of the collectors that I mentioned, and each collector has its own options. Okay, so it's very customizable. You can do a lot of different collections, okay, from any system. And then we have the profile file. The profile file is used to define the list of artifacts that will be collected. It's also a YAML file. So the profile file has a header, has the list of artifacts that will be collected in the order they will be collected. Okay, so volatility information first. Then you can add a group of artifacts. You can add a single artifact file. You can even select a whole folder and then exclude some specific artifacts as well. Okay, so it's very customizable. So as you can see, UAC provides quite a few options in the right here that can be used during the execution. For instance, if you know or have a clue when the incident occurred, you can use the --date range start and or the date range end to limit the number of files and logs that will be collected. So the output file will be smaller and easier to be transferred. Okay, you can also transfer the output to a S3 bucket using a pre-signed URL or via a STP server as well. You can use keys for transferring via SFTP, okay? Again, please take a look on the project documentation page for all the available options you have during the collection, okay? Let's talk about the output files. So the default format for the output file is UAC dash the hostname dash the OS dash the timestamp. This makes the collection, I mean, easier identified. So you can you have the host name, the OS, and when the collection was done, just checking the file name. So by default, UAC will create a log file and a tar.gz file, okay? But when gzip is not available on the system, and I have seen that, UAC will just create a tar file for you. And even if there's no tar available on the system, and I have seen this already on some compromised systems where the malicious code deleted a couple of built-in commands from the system, UAC will create a folder and copy all the collected data to that folder. So this way you can SFTP or SCP the files to your forensic workstation or whatever the place you want, okay? What about the acquisition log? The acquisition log is just a text file, okay, that has some basic information about the acquisition, such as the case information. You can set this information on the command line when you are running the tool, okay, if you want to identify the case number, the evidence, the description of your case. It also holds the system information, like the operating system for that collection, the architecture, the host name, the acquisition information, so the mount point if it was run on a mounted image as well, the acquisition start and finish date, and I think the most important one, the MD5 for the output file, okay, for your conference. Okay, let's take a look on what's within the output file. So this first folder here within, so when you decompress the contents of the tar.gz, you're gonna see this root folder here in square brackets. This directory contains file collected by the file collector, okay? These files will be collected, as I mentioned, in their raw format and will be placed in their original path as the compromised system or the triaged system, okay? UAC has artifacts to collect system configuration files, log files, user files, such as the bash history, browser files. They will all be placed within this root folder, okay, in the same path they were found in the target system. You can either extract the contents of this root directory, or even what I have been done is load UAC's output file into your preferred forensic tool for processing, okay? I have been using a lot of commercial tools and free tools to process this information for me. So to process browser history files, browser data, user data, login and logouts, log files, okay? You can just dump the output file into your forensic tool as a disk image, and it will do the job for you. And the remaining directories here contain the artifacts collected by any other collector, like the hash collector, stats collector, the common collector. For instance, in this example here, the body file was created on the body file folder. So this one was collected by stat collector. And most of the artifacts collected by UAC will be stored into text files. So in this example here, if you can see the hardware artifacts that were collected, or the artifacts related to the hardware of the compromised system were collected, you can see a lot of text files here. So in this example here, the CPU info command was run, and the output of that command was stored in the CPU info.txt. So this makes the output easier to be found, okay? So also quicker if you need to identify what you are looking for. So if you are trying to search for a specific common output, you can just take a look on the output here and identify your command or your artifacts pretty quick. Also, I think you guys noticed there's this stdr files. This is basically the error redirection. So for any command that is ran on the compromised system, UAC will also store the error messages, okay? So this way you can check and investigate why a specific command failed, or if any errors were raised during the triage. The UAC.log. These logs holds information such as the command line used when you run UAC, the system information, the options that you use it on the uac.conf file, the available system tools, such as if tar was available, if stat was available, so you can have information about what kind of system you were triaging. UAC ensures that all operations are logged, and any errors can be identified and further addressed by the analyst. So besides that, if we scroll down a little bit, the UAC log file, all the commands ran on the systems will also be recorded, okay, with their own timestamps. So in this example here, we can see UAC started to triage the system and started by collecting information from process listing, running a couple of PS commands with different parameters. And then on the second screen here, we can see trying to find some information for the Linux MRU artifact. So you have the complete snapshot about what happened and when UAC collected that kind of artifact, okay? So let's do the fun part here. Let's investigate, or I think the best way to show you some of the artifacts collected by UAC is by analyzing a real compromised system, right? So let's go. One of the first places I would go when I need to analyze a compromised server is the process listing. I think most of you would agree, right? So you can see here on the left, UAC collects the process listing using different commands, different parameters, and this is why. Because to give you the analyst that as much as information the script can to provide you with this information. Another important artifact is the full path of the running processes. So as you know, the EXE file within the proc PID is a symbolic link to the actual path name to the executed command, right? So in this compromised system here, we can see that the binary file NTP client was executed from an uncommon directory, right? Dev SHM, and it also shows the binary was deleted from disk. Very suspicious, right? So this is a common technique used by attackers where malware is installed, executed, and then deleted from disk. So no remnants are left. The malware will continue to run and execute will no longer appear, the executable will no longer appear on the disk. So why they use this? Because dev /dev/shm is our word writable directory that only exists in memory. So its content will be lost when the system is shut down or rebooted. It's a convenient place to store malicious code, don't you think? So let's take a look on this malicious process here. UAC will also collect or try to make a copy of the proc PID folder. So UAC will collect a lot of information from that folder, which is very useful for your investigation, like the file descriptors, the common name associated with the process. UAC will also collect or make a copy or try to make a copy of the deleted process using DD. As this process is probably a malicious file, UAC will collect it using DD with an option conv equal swab. This option makes every pair of input bytes to be swapped. Okay, so if you want to revert back, you need to use that option as well. UAC will also collect the strings for running process and so on. A lot of information from the proc fs. For Linux systems, obviously, some systems do not even have the proc file system. UAC will also make a copy of the open files when UAC identifies the process has been deleted. So when the process has been deleted from disk and is still running, it's suspicious. So what UAC will do is check all the files that are being opened by that specific process, malicious process, and make a copy of them as well to help you with your investigation. Another nice artifact is the hidden files and directories. So in the Unix based systems, a hidden file is nothing but a file name starting with a period, right? Either a file or a directory. So you cannot see those files, those hidden files, with the normal ls command by default, unless you use the -a option. Attackers will sometimes try to hide their malicious code as hidden files and directories. However, hidden files and directories are not so common outside the user's home folders. We know the user's home folders have a lot of hidden files and folders, but outside that, it's not so common to have hidden files and folders in the file system. So in this example here, UAC collected all the hidden files, and we can see some suspicious files in some word writable directories, right? And this is also another artifact that is collected, the list of word writable files and directories. So in this example here, we can see some in TMP and one in var TMP. So if you noticed this on a compromised server, yeah, take a look on them because they are very suspicious. So let's go back to our suspicious process, I would say. Hopefully in this system that I was triaging, there is netstat available. So let's take a look on the netstat output. We can see here, according to this output, the process has established a remote connection to this IP here, 194.131.98.244 on port 443. But okay, Thiago, but you mentioned in the beginning of this presentation, netstat is not always available on some Unix systems. Yeah. So for instance, for DFIR, UAC will use another command to retrieve the network connections. And for the most recent Linux systems, it also uses SS, the socket statistics commands. And the socket statistics commands, or the SS command, is pretty the same as netstat. So UAC will use both netstat and SS to collect information about open ports. And as you can see here, again, UAC will collect the same command, or the same information using different parameters. So you can have different views for the same artifact that you are looking for. And then just throwing the IP into VirusTotal, we can see it's really associated with a malicious activity. Let's talk about timeline. But before that, let's talk about the body file. Timeline analysis is useful for a range of investigations types, and often use it to answer questions about when a computer was used, or what events occurred before or after a given event. I believe most of you are familiar with the body file format. It's basically a CSV file that uses the pipe char as the delimiter instead of the comma. In order to enhance the timeline creation and analysis, UAC will extract the file system metadata information for you from files and directories using the stat command to create a body file. So here's some examples of body files created by UAC on different systems and file systems. So no matter what the file system is, the system, or the architecture, UAC will try to create a body file for you, so you can load into your preferred forensic tool like mactime or Plazo. So how UAC collects the body file or the metadata information for AIX and Solaris, for instance? Because I don't know if you guys are familiar with AIX and Solaris, but they do not have the stat command. So you cannot extract the same information as in a Linux, a FreeBSD, a macOS. So UAC comes with a per-based stat version. Okay, so if the stat command is not available on the system that you are triaging, UAC will try to create the body file using the stat per version instead, and the output is exactly the same. So let's back to our case again. As I said, the body file is very useful when you are trying to create a super timeline. For this presentation, I used Plazo to parse UAC's output file for this server here. And Plazo did a great job parsing all the artifacts, including the body file. But you can use your preferred tool. I created a plugin for Axion as well to parse the body file. You can go to Magnet's page and download if you are familiar with Axion. So after processing the output in Plazo, you can use either a Microsoft Excel or this awesome Timeline Explorer tool by Eric Zimmerman to analyze your data. You can even ingest the parsed data into TimeSketch. As you can see here, Plazo parsed the log files, the WTNP, which stores information about logins, logout, and also Plazo was able to parse the metadata information collected by UAC. So this is your timeline will look like pretty the same as one created from a full disk image. But super timeline can be huge, thousands of lines. So it would be good to have a pivot point to start with, right? Like a keyword, like a process name, or even better, the date and time when the malicious process is started on the compromised system. So hopefully you can use PS to get that info. So UAC will do this for you. In our example here, the malicious process 43396 started at 10:33 a.m. on a Friday, July 15th, by the Tomcat user. But how about the time zone? The time zone can be checking the date.txt file, which is another artifact collected by UAC. Okay, moving back to our super timeline. We can use the date and time when the malicious process started as our pivot point. So let's take a look on a few lines here. So remember that the malicious process started by the Tomcat user, right? So as you can see here, the Tomcat user logged into the system seconds before the malicious process started. 2 seconds after that, we can see some suspicious files being created on disk. These files we already identified earlier today, right? Using the hidden files collector and the word writable collector as well. Let's continue with our analysis. More files here being created just before the process was ran. So, I mean, super timelines and UAC are very, I would say, super timelines are very useful for triaging and identify what was done. And with this body file collected by UAC makes your life easier, because you're also gonna have information about files being created, changed, accessed, and in the file system. Okay, as part of the collection, UAC will also hash the executable files, okay, of all running processes. In this case here, we have the hash for the suspicious file, which I also throw into VirtualTotal, and boom, it's related to Mirai botnet, okay? Before we finish, I would like to mention some additional features provided by UAC. If you're triaging a system that is running containers, for instance, either using Docker or Podman, UAC will make use of them to collect artifacts for containers. UAC will also collect information such as the list of containers, if they are running or stop it, when they started, the list of exposed ports, everything for you. Also, UAC will collect information or artifacts from each running container. So UAC will loop through the existing containers and collect logs, collect network information, and so on for you, and storing the output file. This is extremely useful when we are triaging a server running hundreds of containers, right? So it's handy. Snap and flatpak. Snap is mostly used was created by Canonical. It's mostly used in Ubuntu, and flatpak is mostly used in Red Hat distributions, right? Both package formats are being widely used today, and forensic tools need to be prepared to collect artifacts related to them. Let's take a look, a closer look on this Telegram artifact. So in the first, on the red square here, says UAC will collect the log.txt file on a normal path if the Telegram application is installed using the built-in package managers like apt, dnf, yum. The second one and the third one here are related to flatpak and snap. So UAC will also is also prepared to collect information from snap and flatpak applications. Creation time for ext4. Okay, this is interesting. Most Linux systems will not provide a creation time or birth time for a file or a directory via the stat command. well, there's a debugfs approach, but it's not practical. You need to do a lot of steps, a lot of commands. So what UAC does is UAC has its own tool, StatX. StatX uses a system call that was introduced since kernel 4.11. So if the system is running kernel 4.11 or newer, UAC will try to run StatX to retrieve the creation date for files and folders. Okay, so this is very, very useful for when UAC is creating the body file. You also have the creation time for ext4 files, okay, if the kernel version is 4.11 or newer, which is awesome. To finish my presentation here, last but not least, the memory acquisition. Memory analysis is a powerful forensic technique, but acquiring memory dump from Unix-like systems has been proven to be challenging, right? I think you guys agree with me. So UAC uses Microsoft AVML tool to create memory dumps for Linux systems. Unfortunately, this only works for Linux, okay? After the collection, you can use your preferred tool to parse and analyze the memory contents, okay? So if you want to find more information about UAC, please visit the project's repository, the project's documentation page. I invite you all to contribute to the project, either creating new artifacts, submitting new profiles, proposing new features, and even reporting bugs. Okay. A special thanks to the IBM CSERT and X-Force guys that have been supporting the tool since its beginning. Thank you, Sams, as well. Feel free to contact me in LinkedIn, Twitter, or in the Digital Forensics Discord server. And good luck and have fun during your incident response engagements. Yeah.